All right, everyone, welcome to today's WiDS Datathon Challenge number 2 winners panel discussion. We're really excited to have you all here today to hear from our Datathon winners. Feel free to introduce yourself, put your name, where you're from in the chat. We'll use the chat today to engage with the panel and engage with the winners. And so my name is Valerie Elliott. I am your WiDS Datathon program director. It was fantastic to put on a second challenge this year for the first time. And I am also here today with Sharda. Sharda, would you like to introduce yourself?
Sure. Thank you, Valerie. Good morning, everyone. My name is Sharda Kalanidi. I'm Technical Director of the WiDS Datathon. I've had the privilege of being involved with the Datathon, particularly the dataset preparation piece for many years now. And I'm always super excited to meet the winners and hear the solutions.
Wonderful. So this year in the WiDS Datathon Challenge number 2, our participants analyzed an oncology data set that was provided by Gilead Sciences. And they looked at how climate patterns impact access to healthcare. And so whether or not you participate in this year's challenge, we hope that you learn a lot and benefit from hearing from our winners today. It was a really fantastic challenge. We had a lot of first-timers and beginners participating from around the globe. And feel free to put in the chat if you participated in this year's challenge, let us know in the chat. And so today we have the pleasure of hearing from each of the 6 Datathon winning teams. And so one representative from each team will take about 10 minutes to share their team's results and findings and learnings and interesting things they learned and gained throughout the competition. And after the presentation, we will follow this up with a short Q&A with Sharda. And so if you have any questions for the winning teams, please put them in the chat. The rest of the teammates will also be joining us in the chat and available to engage and answer your questions. All right, so let's get started with the first team and bring up the slide for the first presentation. Great, so we will start with the first place team, 256 from Kampala, Uganda, and Rebecca Achala will present on behalf of her team. And so I'll pull up Rebecca here and we'll get started. Go for it, Rebecca, whenever you're ready.
Thank you, Valerie. I hope everyone can hear me.
Yes.
Hello, everyone. My name is Rebecca Achola, from Uganda, Kampala. And yeah, well, we are very excited, thrilled to have come first. Together with my partner, Emmanuel Ogwal. So I'll just go ahead and give a brief introduction of our team. So as I said, my name is Rebecca Achola. I am a graduate of Statistics and Mathematics from Uganda Matters University. I also have a certificate in Data Science and AI from the Tech for Dev. It's a Nigerian institution, an initiative of Microsoft and FinTech and all that, yeah. And this was my second competitive data science competition. I had participated earlier in a cargo competition by Policy Uganda, and I came 11th out of 20. And then this was my second one with my teammate, Emmanuel, who is a graduate of economics from Chambogo University. He has prior experience. He has more experience in data science and cargo participations. He has participated in different competitions and on cargo, Zindi, Data Camp. So he has very, very strong programming skills, and he's a practicing data scientist. Next slide, please. Okay, so an introduction of our model. So we use the Cat Boost model for the feature selection, and we chose 10 features that were most relevant. We found they were most important in building our feature selection model. Some of them include breast cancer diagnosis code, the patient age, metastatic cancer diagnosis code, to mention but a few. Our tools were Python, CatBoost, sklearn, and a Jupyter Notebook. The runtime, as you can see, was 1,124.9 seconds. That's roughly 18 minutes. Next slide, please. So our feature selection or engineering. So as I said earlier, we built a baseline model specifically for feature selection, which were 10 slides. We chose 10 slides from 10 features. From the features, we changed the data types from categorical to object. From object to categorical data type, I beg your pardon. The missing values we filled in with the word missing and let CatBoost do the encoding. We also tried, at first, initially, we tried to fill in the missing numerical data types with the mean, but however, it was the model was performing poorly. So we decided to just let it go. And then we just let CatBoost handle it as well. And then we created a new feature called class. And we got this from the notebook of the previous winners, the first winners of the first datathon. So since my partner and I, we're not domain experts, we simply read the write-up of the winners of the previous datathon, since the two data sets were a bit similar. So emphasis, though, is made on the fact that we acknowledge that it was their write-up that helped us to come up with the class. So how we came up with class, during feature selection, the metastatic cancer code was among the top 3 most important features, because the length of the code in this feature was 4. Like this feature had the code was length 4. So what we did, we extracted the codes that have length of 4 and formed it and named it classed. So that's how we came up with the feature called classed. Next slide, please. That is an illustration of the feature importance. As you can see, the breast cancer diagnosis code was the most relevant, and we used the first 10 from the bottom because they were the ones which seemed most important. So yeah, those are our feature importance and engineering. Next slide, please. The training methods. So we plotted the distribution of the target variable, and it was a Poisson, I beg your pardon my pronunciation, Poisson distribution. That was the distribution of the variable. So we decided to use the CatBoost method, the CatBoost model, and we trained it on a 15 stratified k-fold cross-validation. What we did, we chose the parameter, the target border count, which was this parameter that helped us to win the competition. Now, let me just try to explain what this parameter is all about. So we use quantization for encoding the categorical features. So the parameter, target border count, controls the maximum number of borders to be used when creating bins for the target variable during the quantization. These bins are used to determine which category the data point belongs to based on the target variable value. What CatBoost usually does is it analyzes the target variable and determine its median, I beg your pardon, the median. It determines its median. And then it will create bins around the median. And the number of these bins is determined by the target count border, the target border count, I beg your pardon. So in case you need further information about quantization, we also added a link of the resource in our write-up that we uploaded on Kaggle. Next slide, please. Okay. So while most participants spend most time looking for stable cross-validation, my teammate and I agreed that encoding or even transforming features leads to a better model. This was the case. This was our case when we encoded the categorical feature with the control target border count. The climate data did not seem to have much of an impact in access to healthcare because we realized that they were not really predictive. The features were not predictive much, as much. And that's illustrated below in the next slide. As you can see, the climate data was not really predictive as such compared to the other features. Next slide, please. Okay. Our simple model, the breast cancer diagnosis code, the patient age, metastatic cancer diagnosis code, the patient race, would give us a 90 to 95% performance with the single cut boost model. The amplified model gave us a root mean squared error of 81.008. And that is it. Thank you.
That's great. Thank you very much, Rebecca. It's a very interesting presentation. And we're always, really amazed by the perspective that our winners bring. We'd like to start off by asking you, so thank you for explaining, your background and your teammates' background. Did you feel like you guys had, different skills or complementary skills, different perspectives? How did you work together in creating this solution?
Oh, as I said, we met on Twitter, actually. We met on Twitter, and that when we realized that we both have a passion for data science, I had made a post. I don't remember what exactly I posted, but I posted a problem that I was experiencing and I was looking for help, and he replied. So that's how we met, and then he started helping me because, as I said, I'm new to data science, maybe a year or two. So I was participating on a competition on data camp, and he helped me, like, make some modifications and things like that. And then I think, yeah, we have complementary skills because he's an economist and a data scientist, and I'm a mathematician. So I think those two skills help us balance and work together.
That's fantastic. One more question. You said, the most important thing was you chose the target border equals 10 as our encoding parameter. And this
Yes.
and you explained this. Can you explain is there an intuitive interpretation of this parameter, or is it strictly for sort of tuning your model? Can you actually interpret this?
So as I said, it determines the number of bins that you can, yes, it determines the number of bins, and it gives you a variety, a range from 1 to 255. And my partner and I decided that we will choose 10 as the most suitable to help us predict the model perfectly.
Is there a reason for that? Was that the best fit for the data? I'm just trying to understand why you chose this parameter as 10. Was that the best fit? Was there a distribution? Was the data skewed? Was there something about the distribution itself that this parameter was really was good to use this parameter?
Yeah, we did some research on the distribution when we found it was a Poisson distribution. And once we decided that we shall use the cut boost model, Emmanuel was, this was more of Emmanuel. He was very certain that 10 would be the most perfect number to use.
Well, that's awesome. That's fantastic. Do you have any further insights? Anything else you'd like to share with us?
Pretty much that's it for now.
Yeah.
Yes.
Well, thank you very much. I think that was really interesting. Thank you for your presentation. It was very insightful. And we look forward to seeing you again in future competitions.
Thank you so much. It's a pleasure.
Pleasure. Thank you, Rebecca.
Welcome.
All right. Wonderful. Next up, we have the second place team, Team Perceptron from Bangalore, India. And Sharon Sujitha will present on behalf of her team. There you are. All right, over to you, Sharon.
Hi, everyone. I would firstly like to thank the WiDS Datathon team for arranging such a great hackathon, and we are glad that we won the back the second prize. And I'm Sharon Sucheta and my teammate is Chandan Kumar. So our background is that we both of us hold bachelor's degree in computer science. He has done his computer science and engineering from NIT Surathkal, and I hold a bachelor's degree in computer science engineering and specialization in AIML from SRM University. So both of us are from India, and we currently work for Wells Fargo. And we've also worked on AIML projects before during our undergrad, which has helped us to learn how to work with data sets and using data manipulation techniques, feature engineering, feature selection, and trying out different models and participating in few competitions before has also helped us in gaining experience in how to solve machine learning problems and deep learning problems. And Chandan is an expert in programming also. That is to be mentioned. So I'll get on with the training methods used. So we've used HIST grading, boosting, and sample grading boosting, and then nearest neighbors, rich regression, random forest regressor, extra trees, XGBoost, CatBoost, LGPM, light GPM. So basically, we have used regression and more of tree-based models. And the next is for most important features we used is ICD, BMI, race, pair, and state. I'll
You
come
want to
up.
share? Is she going to share her presentation?
Yeah, we can see the presentation.
Okay. Sorry, don't mean to interrupt. Go ahead.
That's right. So I'll explain how we came up with those features. Then we have breast cancer code diagnosis, breast cancer diagnosis code, metastatic cancer diagnosis code, and patient age. So the tools we used were Python and Python-based libraries, NumPy, sklearn, Pandas, and Colab, and Kaggle notebooks to execute the project, and Optuna for hyperparameter tuning, and many more. So it took around 30 minutes to train the model in our laptop. So to complete the full notebook. And can you go on the next slide, please? Next, yeah. So for data imputation, we tried out different approaches. First, the first approach was to consider all the missing values as a different category, and that helped us in preserving the information, but it was not sufficient enough. So secondly, we tried to fill the missing values with the median for numerical features, and for categorical features we try to fill in with mode, so which provided a baseline imputation but lacked in sophisticated predictions. So we looked for a better approach, and what worked for us was imputing each feature individually. So we considered pair type, BMI, and patient race. So in pair type, we found that people generally above the age of 65 are typically covered with Medicare Advantage. So we fill the missing values first for patients above 65, and then, which almost covered 500 out of 1,300 missing values for the feature pair type. Then for the remaining values, we created age bands of 0 to 22, and then 22 to 44, and so on, as mentioned here. And then we imputed the missing values with the pair type within with the mode of the pair type within the each age group. And then coming to BMI feature, we using the same age groups, we imputed the missing BMI values with the median BMI of the respective age groups. Then for patient race, we filled the missing values with the mode of the patient race grouped by the patient's zip code. So and next for feature engineering, feature selection, for breast cancer diagnosis description, since this feature had more what do you say, contain more textual information. So we tried to use several techniques to convert it. So first we used TF, IDF representation. Then we went on to extract the important terms from the text. And then we created a single binary feature. And then we concatenated all the features built from the text into a single string feature. So this approach yielded the best result for us for the feature breast cancer diagnosis description. And then for temperature features, we observed that we observed that the temperature for each month remained consistent across years. So we using feature important analysis, we found that the months May, June, July, August, and September were the most influencing months for the target variable. So can you move on to the next slide, please? And yeah, here for ICD features, what we did was we created additional features from the ICD code. So we created ICD state, ICD pair, ICD BMI, and ICD race. So we created these by grouping these variables with ICD codes, whether it's based on ICD 9 or ICD 10. So this actually improved our performance very like it showed a very great performance after we implemented this technique. And then coming to feature selection, we used feature importance metrics and sharp values to identify the most important features and like relevant to the project. And then we and also utilized a sequential feature selector. This helped us in getting the best set of features for each mod based on each model. It was used for tree-based models to optimize. And then next slide, please. So yeah, this is a variable importance plot, and here type is our breast cancer diagnosis code, which we have imputed as type based on the ICD codes, and ICD pair, race, and BMI show of most importance, and followed by the other features we have used. So can you move on to the next slide, please? Yeah. For training methods, as I have mentioned before, we applied various regression and tree-based algorithms. So we used ridge regression, KNN, and random forest trees, gradient boosting, HIST, gradient boosting, XGBoost, and CatBoost, and so on. So we assembled all these models. So we utilized Optuna to optimize the weights for ensembling the models. And then this helped us in minimizing the RMSE, which is a root mean square error. So between the target variable and the sum of predictions. So we also, one more strategy of ours was to keep minimal discrepancies between our validation score and a training score, so that our model doesn't overfit. Because this was also a learning from a previous edition of the WiDS Datathon. We understood that there should be minimal discrepancies between both the scores. So that was also one of our strategies, which I think helped us to gain a good performance in our second season. So next slide, please. Yeah. So the important interesting findings for us, as I mentioned before, we had used some features for our data imputation techniques like patient race, BMI, and pair type, because these had more missing values in the data set. We thought skipping this might not be the best idea, and plus we also tried without these and with these, but we got good results including these features and filling the values based on the imputation technique strategy I had mentioned before. And also additionally creation of features like ICD, BMI, pair, race from the ICD codes also gave us a better understanding and better results and improved the performance. So also we use the temperature feature when we were able to identify May, June, July as a important analysis, and we have also included that. That's something which we did differently, and which might have also helped us in our performance. And these were our important findings, and for a simple model. Yeah, in using these features, pair type, patient age, diagnosis code, and metastatic cancer diagnosis code, and the income household, which also could potentially yield to the result to for the results to range in around 95 to 98% also, RMSE, similar to what we have achieved. This could have been achieved with a simplified model, like just using one model cat boost, something similar, which would score up around 80.93 on a private leaderboard, approximately. So yeah, I think that's it from my side.
That's fantastic, Sharon. That was a great presentation. Really happy to see the hard work that went into this. And we want to just kicking things off. A quick question: you said your background and your teammate's background was computer science, and do you think that prepared you adequately for this competition, computer engineering, or do you think that there are certain areas or concepts that you had to learn yourself? You had to teach yourself to supplement your sort of background.
Right. So yeah, definitely our background in computer science did help us with programming, because that gave us a strong base in programming and coming up with a solution, like thinking, because we were good at data structures, which helped us in algorithm, finding a good algorithm technique. So, but we did have to learn a lot when it comes to this competition. Just having a background was not enough. We had to learn and apply specific tools, like how to apply specific tools and frameworks like Optiona for hypermeter optimization, because I did not know about this before. And then also using sharp values for model for interpreting the model, and then because these were some tools which were important for fine tuning and understanding the impact of different features. And also we had to explore more models other than the usual models we had worked on in our projects before, like light GBM, hist gradient, because that was one of the best performing features for us. And yeah, so we did have to learn a lot apart from that. And also discussion posts from the previous edition. We did researching that also. We through that there was a lot of learning and knowledge we gained through that. That is also something I would like to mention here.
Yeah, I think it's really interesting. My background is mathematics, and it's really interesting to hear, computer scientists come at the same problem from a different perspective. And it's like you meet in the middle and you hear, how they approach a problem is very different from how, sometimes it just meets in the middle. So it's really interesting to hear, how you approach a problem and what, everybody needs to learn, so it's really interesting, the areas that you need to focus on and that you learned. And did you tap into the resources from WiDS at all, or Kaggle to help supplement your education as you built this out?
Yeah, the resources from Kaggle was really helpful, as I mentioned before, especially discussion posts from the previous edition. We could because the techniques which they had used for feature engineering, the winners from the previous edition, that also helped us to try more and more to get. And we also one more thing which my teammate Chandan, he found that overfitting the model is gonna even if it gives a good score in public, it's not gonna give a good private score. So he was the one who found that out, and he made sure that our model is not overfitted. So this is something we learned from the discussion post itself. So that is a major thing which helped us, major learning, which also helped us in winning the second prize, I would say.
Yeah, that's awesome. You said you had worked on a range of models in ensemble gradient boosting, his gradient boosting, a lot of them I won't list them. Can you please describe the relative performance of each of these models? Can you compare them like broadly, regression trees? What did you learn from these different modeling approaches? And can it sort of summarize some of your learnings from them?
Yeah, sure. So we did use a range of models. So out of that, I would say the best performing ones were his gradient boosting and cat boost following that, and also random forest. So these were the top performing models out of all the models. And each model had its own advantage. For example, his gradient was performing efficiently on large data sets. It usually performs well on large data sets, and the results are comparatively faster. And cat boost also is it performs very well with categorical features, which is required here for the diagnosis code, and it requires less processing, and it performs on par with XGBoost and like GBM2. So in summary, I would say the tree-based models were able to capture complex relationships in the data which we have. And ensembling all these models helped us basically, if we use one or two models, it might be prone to the noise and error in the data in that set of data. So if we use the more models we used, we also found that the data would be more prone to noise and error, so that it will work better on unseen data when it's being tested, and which reduces the variance and bias and the noise in the future predictions. So that is something which we found by assembling all the models. And if it's just a simple model, it might be simple to capture the underlying data. So that might result in high bias, and that might fail to represent the complexity of the data adequately. So assembling all more models helped us in reducing the variance and bias.
That's awesome. That's fantastic to hear your approach, and I'm sure that audience will be really interested in your in your code, in your Python notebooks, and how you went and approached it. Thank you so much for your presentation, and congratulations again on an outstanding performance. And we look forward to seeing you again in future competitions.
Thank you so much. It was a great time for us too. And we had a good learning experience from the competition. Thank you so much for this opportunity again.
Thank you very much. Yeah.
Congratulations.
Thank you.
All right, thank you, Sharon. Next up, we have the third place team, Olga Skvortsova from Pennsylvania here in the United States.
Hello, thank you for having me here. So my name is Olga Skvortsova, and I would like to start my presentation with telling a little bit about my background. So I received my master's degree in computer science from now well-known School of Computer Science at ITMO University. Then I worked as a systems administrator at St. Petersburg Stock Exchange. And after I moved to the US, I created a company called Unfilter Shop. This company specializes in the development of components and custom solutions for Microsoft search products. My interest in data science started in 2015 when I discovered a machine learning course taught by Stanford professor Andrew Ng. And since then, I took many data science related courses. Some of them are listed on this slide. At some point, I decided that I would like to get a deeper understanding of mathematical principles behind data science and machine learning. And that's when I joined the first cohort of MIT MicroMasters program. I also would like to mention that this is my 4th year participating in WiDS Datathon, and I find those competitions challenging and rewarding, and I'm glad to be part of this initiative. Can I have the next slide, please? So my winning model is the weighted average of AutoML model and the stacked assemble. Stacked assemble itself includes indicator feature, which basically distinguishes between ICD-9 and ICD-10 diagnostic codes. It also includes one autogluon model, one XBoost model, and 5 different stacked assembles, each containing several boosting and bagging estimators. Next slide, please. So one strategy I used in this competition was pseudo-labeling. And some participants noticed it was challenging to assess models' performance using local CV in this competition. So I was trying to find something else to rely on. And since data sets for challenges 1 and 2 came to this from the same data pool, I decided to create pseudo-labels and then use them as features for my models. So the main idea here is I combined 2 data sets, then I trained a model on the combined data set to predict challenge 1 target. And then I use those predictions and as pseudo labels in the challenge 2 models. My hypothesis here was if I create a model that performs well on both private and public leaderboards in challenge 1, it should perform reasonably well for the dataset for the second challenge. It proved to be correct since all of my models improved their performances after I enhanced them with those pseudo features. I also created several engineered features which I used in many of my models. First two are basically derived from IDC-10 diagnostic codes, and they define the location of the cancer. Third one is the indicator variable I already mentioned. It distinguishes between ICD-9 and 10 code types. Next two features are also indicator features. Breast cancer diagnosis indicates whether I cleaned the diagnostic codes during data cleaning, and metastatic first novel treatment indicates if there are record for the patient about such a treatment. The last two features are interaction variables, and they were used in data split stratifications. Next slide, please. So I did not do any data transformations for AutoML or AutoGluon. For XBoost model, I did a variety of categorical encoding, including one-hot, ordinal, and target. And I used ordinal encoding in all my assembled models. Next slide, please. For AutoML and AutoGluon, I used only original cleaned features with pseudo labels. I did remove high VIF features, VIF standing for variance inflation factor, and both models showed improved performances after that. I also did not impute any individual patient-related features. For XBoost model, it was derived from my challenge 1 submission, and there I used a Baruta algorithm for feature selection. And for all ensemble models, I used CatBoost feature selection algorithm. Next slide, please. Okay, so this is, I have 4 plots for 4 models I chose from my final submission. First one is the best XGBoost model from AutoML ensemble. And we can see that the top performing variables would be 4 pseudo labels that I used. Then diagnostic codes, patient age, and also pair type at the bottom. Next slide, please. This is AutoGluon model, and the distribution of features is pretty similar. I used 1 pseudo label, diagnostic codes, patient type, patient age are on top of the list. Next one, please. So this is one of my stacked assembles. So here we see the same thing, diagnostic codes, pseudo labels, patient age, patient type. And here I did not use patient zip3 feature to capture patient location. It was captured using some demographic and temperature features. Next slide. And on this one, this is another model from stacked assemble model. And in this model, I did not use demographic or temperature features. I used only 3 location features, including patient zip3 to capture patient location. And as we could see, basically the ranking of the variables importance is pretty much the same for all 4 models I chose. Next slide, please. Okay, so the model training mostly used 6-fold cross-validation. Stratification was based on different interaction variables. Rich regression was used as a meta estimator in all stacked assembles. And the weights for the final weighted assemble was chosen manually. The overall training time for the submitted model was 7.5 hours, with AutoML taking the longest time to train. Next slide, please. Okay, so a simple model. So here are some root mean square errors for different models. So which one should we choose? The one who stands out is AutoML, because if I submitted it alone, it would be still competitive on the public leaderboard and would give me a better position on private. But if we look closely, it's actually an assemble of 6 models itself, and they're listed on the plot. And the training time is about 7 hours. On the right, though, there are a couple of simple stacked assembles from my final stacked assemble, which, by the way, disappointed me. It did not do well on the private leaderboard. But those assembles, neither of them would win the competition, but if we look closely, each of them has less than 5 minutes time to train, and actually the performance decrease for any of them is less than 1%. So either of them, I think, would be a good candidate for a simple model. Next slide, please. So to summarize, the main three strategies that I used in this competition were pseudo-labeling. I tried to use a variety of data imputation methods, and I tried to use different kind of models with different sets of features. And there are two findings that I would like to share. Plot on the left shows distribution, target variable distribution for two groups of patients, one with ICD-9 diagnostic code type and another one with ICD-10. And as you can see, the distributions are quite different. So we don't know individual diagnostic days for the patients, but what we do know that October 1st, 2015 was a deadline for code system transition. So patients with ICD-9 code types must have been diagnosed before that. So it would be interesting to study if there were any other factors besides the coding transition that actually contributed to such a significant change in the target variable distribution. If you look on the plot on the right, you will see predicted target distribution for the trained data set generated by one of my best models. And if you can see, it's clearly by model, and each cluster represents, again, patients with a different ICD coding type. And they're centered around the target variable mean for each group. All my models displayed pretty much the same behavior, and unfortunately, I was not able to improve it with feature engineering. So I was wondering if maybe this situation can be improved by enhancing the data set with additional clinic level and individual patient level features. Again, it would be a topic for another study. Next slide, please. So this concludes my presentation. Thank you again for having me here, and thank you for listening to my work. If you have any questions, I would be happy to answer them now.
Thank you, Olga. That was a fantastic presentation. A lot of hard work, very interesting insights that you've come up with very interesting sort of working in different models and what you're able to glean from each of these different models. Could you explain for our audience what is the Boruta method?
Yes, this is method that I used to select features for my Challenge 1 competition. So it came with XBoost model that came from Challenge 1 competition. Basically, this is another feature selection algorithm, and it's a wrapper built around random forest classification algorithm.
I see. I'm curious. You had PREDS ENS 203. Do you have any interpretation
yes,
around that?
These are my label feature, pseudo labels, and basically they are predicted probability of whether the patient would be diagnosed within 90 days.
Okay.
And because I used them because of the similarity of the target variables of the first and second challenge, and because of data was taken from the same data pool, I was able to actually use data from the Challenge 1 to enhance my models in Challenge 2.
Very interesting. I think you're one of the only teams that actually did that. And I think you did it very creatively. So thank you very much for your very interesting approach. And thank you for your performance, your top performance. And we look forward to seeing you again in future competitions.
Thank you.
Thank you, Olga. Congratulations. All right, moving on. Next up, we have the top high school team. This is Michelle Hahn from California here in the United States. So over to you, Michelle, whenever you're ready.
Yeah, thank you. Hi, everyone. So I'd first like to thank the Women in Data Science team for hosting such an amazing datathon. It was super fun and a great experience. So my name is Michelle, and when I was working on this, I was a high school junior, but now I'm a rising senior. I'm based in Sacramento, California, and as for previous experience, I don't have much professional experience because I'm still in high school, but I did take a couple related classes at my school, which were AP Computer Science Principles and AP Statistics. I also attended a summer program in my sophomore year called Stanford AI for All that helped me with the introductions of programming and briefly touched on data science as well. And I decided to enter this datathon because I found it very intriguing and inspiring, especially as it empowers gender minorities in the field. And just having some extra time on my hands, I thought this was a great way for me to learn how to apply data science into healthcare. Next slide. So for a brief overview of my solution, I started by doing some basic exploratory data analysis to get a feel for the missing values in the data set. And that information helped me decide imputation strategies to implement. Then I constructed a pre-processing pipeline to prepare the data for modeling. And then I focused on selecting the most relevant features for the model. And then finally, I trained an XGBoost model on the test data and tuned the hyperparameters. So the most important features turned out to be breast cancer diagnosis code, metastatic cancer diagnosis code, and patient age. And as for tools, I used Python as the programming language, and I used various libraries like Pandas, NumPy, Seaborn, Matplotlib, sklearn, and XGBoost, and the total runtime was 30.2 seconds on the Calico notebook. Next slide. So here are just some things I plotted during the exploratory data analysis. This was just a bar chart to see the percentage and number of missing values by the column. Next slide. And here is the same thing visualized in the bar chart. So it just shows the missing values again, but as a heat map. Next slide. And then this histogram just showed the distribution of the target column and just gave me a feel for what the spread of the target value looked like. And I learned that it's highly right skewed. Next slide. So to go more in depth about the feature transformations I applied, I imputed the missing values in the numerical columns by using median imputation, and I used this to mitigate bias that mean imputation would have due to outliers. And then for the categorical columns, I used one-hot encoding to convert them into a binary format that the model can process. And then I also used standard scalar to standardize the numerical features to ensure that each feature contributes equally to the model. And then I ended up selecting the features based on a correlation heat map and domain knowledge. Next slide. And then here is the variable importance plot that was plotted after training the XGBoost model to see the contribution of each feature to the predictions. Next slide. So to train the model, I used XGBoost that was incorporated into the pipeline mentioned earlier and shown to the right. Besides XGBoost, I experimented with other models too, like LightGBM, CatBoost, random forest, and logistic regression, but XGBoost just emerged as the best performing model for me in terms of accuracy on this data set. But if I had more time, I would have definitely looked into the ensemble models, as they've clearly worked very well for the other amazing winners. And then for hyperparameter tuning, I used grid search CV to systematically find the most optimal parameter set. And then for cross-validation, I just used a simple train test split to train on some subsets of data while validating on the remaining data. But in a future iteration, I would consider incorporating k-fold cross-validation to minimize variance in the model. Next slide. And here is the correlation heat map that I was mentioning earlier. So where the squares where the darker colors are, the higher the correlation is. Next slide. And here is just another plot I found interesting because it seemed like the metastatic diagnosis period was quite varied across all ages, but it was the most concentrated between ages 40 and 70. Next slide. And then for the simple model, the subset of features that got me 90 to 95% of the final performance were breast cancer diagnosis code, metastatic cancer diagnosis code, and patient age. And the simplified model score was 82.56, which was slightly higher than my final score. Yeah, I'm open to any questions.
Thank you, Michelle. That was fantastic. Really amazed to see high school students really come up to this level of performance and really a rigor in their competition submissions. I'm wondering for our audience. I mean, you stated some of the things that you've done to sort of teach yourself and learn about data science, and you had been to different sort of sessions. Do you think you're largely self-taught, or what are some of your explorations or things that you can point to our audience, pointers like resources that they could use in their own development, or things that you can help you can say the high school students around the world who might be listening to you?
Yeah, so I think I definitely got a solid foundation for just programming in general through related classes like the ones I mentioned earlier. But I feel like data science is definitely a little bit different. So I obviously had to learn a lot on the way for this competition. And it was a little bit of a challenge, but in a good way. And I definitely learned a lot from that. I think the resources linked on the challenge itself, I think on the Kaggle website, were really helpful, not only for knowledge pertaining to this data set, but also just for data science in general. And obviously looking at the discussion boards and seeing the insights that everyone else has contributed quite a bit as well. And yeah, I think for the rest of it, it was kind of just self-learning, trying to see on YouTube what others have done, or just looking at Stock Exchange and stuff like that.
That's awesome. I love to see your correlation analysis. Did you explore other multivariate analysis techniques, maybe like PCA or anything else, or is that something you might explore in the future?
Yeah, so I did not explore the multivariate techniques when I was initially doing the competition, but if I were to do it again, I think techniques like PCA would definitely be very helpful in reducing the dimensionality and minimizing the noise and redundancy in the data, which could have helped the model focus on the most important features.
Well, that's awesome. Thank you for your presentation, Michelle. Congratulations on a fantastic performance. We look forward to seeing you again and again in the future. And thank you for really being an inspiration for high school students and coming so far. That's really fantastic.
Thank you so much for having me.
Absolutely.
Congratulations, Michelle. Great. Well, okay, next up, we have the top student team, UMFMG Underdogs from Romania, and Krina will be presenting on behalf of her team.
Hello, everyone. My name is Mihai Ștefania Krina. I'm from Romania, Europe. On behalf of our team, we want to express and gratitude for winning the top student team in this year's second challenge. We would also like to congratulate all the winners and participants for their hard work. You already know the topics that I'm going to talk about, so let us introduce our team. We are 4 medical students in the second year at University of Medicine and Pharmacy Grigore Popa from Iași, Romania. We have no prior background in data science or machine learning, but we took C++ classes in high school and participated in many projects along the way. My colleagues are Mitric David, Panait Andrei, and Nedelcu Andreea Demetra. Andrei also has experience in personal full stack and automation projects as a hobbyist. Now let's talk about the summary to our solution. The training methods we used are ensemble of CatBus regressor, XGB, LGBM, AdaBoost, KNN, LGBM with 2D objective and his grading regressor. The rich cross-validation was used as the meta learner. Most important features regarding the patient include breast cancer diagnosis code, patient age, metastatic cancer diagnosis code, age group, and pair type. The temperature features consists of average of August 2016, variance of winter 2017, range of autumn 2013, and variance of winter 2016. Regarding the demographic features, they refer to self-employed and education some college. The tools and libraries used are Jupyter Notebook, Pandas, NumPy, sklearn, and Matplotlib. And the average model runtime is about 10 minutes on Giga Cloud. Moving on. This is a representation of the future importances. You can see that the most important code, the most important one is ICD-9 code. It's a breast diagnosis code. I will talk about it soon. I have already presented the most important features. There are some important feature transformation that had a major impact on our score. We had to fix the zip code anomalies because some patients had demographic values that corresponded to a different zip code, while others had the incorrect state or division. We also remapped the diagnosis code because there were female patients who had male diagnosis codes. And the imputation of average monthly temperatures, we used the temperatures of the previous or next months and added the demographic and pair type columns using mean or mode of all the patients with the same zip code. There were some cases when it didn't work, so we had to look for the same state. I will try to explain the ICD format. There is the ICD-10 format. For example, C50-611. The first three characters represent the prefix. C50 means malignant neoplasm of nipple and areola. The fourth character indicates the location. It can take values from 0 to 9x7. For example, 6 means axillary tail of breast. The fifth character represents the gender, 1 for female and 2 for male. The sixth character is the side of the affected breast, 1 for right, 2 for left, or none for unspecified. For ICD-9 codes, which are less granular and descriptive, for example, 1741, the first three characters mean malignant neoplasm of female breast, and the rest of the characters indicate location, one meaning central portion. After understanding these codes, we binary classified the breast cancer diagnosis code and organized the ages of the patients into bins. Regarding the training methods, our cross-validation strategy involved using K-fold with 10 splits. We tried different models which worked for the community plus additional models that we thought could improve our score. Over half of the tested models hurt our local score, so they had to be removed. The early decision to use a pipeline to handle pre-processing helped us organize our workflow. On one hand, when time came to evaluate the impact of each feature, allowing us to easily add or remove steps in our pre-processing workflow. And on the other hand, by helping us avoid data leakage between the train and test data sets. Our hyperparameter tuning strategy involved using grid search cross-validation on a selection of models. Between the long-running times and mediocre results when trying to tune our best-performing models, we decided to only use it on our worst model, which was KNN, and it yielded satisfactory results in our local CV score. Some findings that we consider interesting. Having read the discussions from the first challenge, we decided that the best approach we could take was not rely on the public score and use a number of diverse models in the ensemble to hedge our bets. Another addition which helped us get the most out of our models was including a set of engineered temperature features such as variance and range for the different seasons. An encouraging finding was that removing all the geodemographic columns led only to a minor increase in public RMSE, suggesting equitable treatment between the same zip codes and states. Removing the temperature columns led to a more pronounced RMSE, increase of RMSE, both local and public in the 02-03 range. Although there was a significant increase in the leaderboard, we were unsure about the real-world impact. And the simple model, using an ensemble of breast cancer diagnosis code plus all features engineered from it, we were able to get 97.87% out of our final performance. Using only one feature, breast cancer diagnosis code, we achieved 97.75% of our final results. And using CAD post regressor on the simplified one-column data frame, we achieved 97.68% of our final result. And that being said, thank you very much for your patience and attention.
Thank you very much, Mihai. It's very interesting, your presentation. I think of all the teams, you all have a very unique background, that you all are doctors are future doctors, and you come with domain expertise, with some kind, at least a perspective on how to medically assess the situation, and you also bring in data science and machine learning background. So I'm really curious for our audience. I mean, can you sort of explain how your background influenced your thinking and how you approach the problem first? I mean, I think machine learning, data scientists will just plunge into and build a model right away. But coming as doctors, how did you actually think about the problem?
Actually, I think that having a background in programming guided the way
Okay.
we analyze the data. We just pay more attention to the details or to the details in the data sets or the mistakes we made along the way. It's true we were familiarized with coding, but not in Python, and we only read about machine learning, hardly ever tried it. So even if it was a lot of effort, we took it as a challenge and expanded our knowledge in data science.
That's great. You're one of the few teams that actually found temperature features of very high in importance. I think one of two teams. And you dwelled a little briefly on that. Could you talk a little bit more about the feature engineering transformations that you did about the temperature variables?
Sure. We try to capture information regarding the average monthly temperatures that could indicate if a zip code had extreme climatic conditions, which we assume would impact the target variable. To that end, we employed variance and range, which we clustered around seasons. It felt natural to us to group the data around seasons, and actually it ended up working great for us in reducing the noise in the data and giving us a more meaningful feature.
Yeah. Well, excellent. Thank you very much. I think this was a very insightful presentation. Congratulations again on a fantastic performance. I look forward to seeing you again. And thank you for your presentation.
Thank you very much.
Thank you, Karina. And congratulations to you and the rest of your team. Great. All right. Last but not least, we have the top first timer of the WiDS Datathon team. This is their first time participating in any of our Datathon challenges. Team DynaMinds from Hyderabad, India. Pujangi Gadakar will present on behalf of their team. So over to you, Pujangi.
Thank you very much. Hi all, thank you. Work in Wells Fargo, and we are a mix of software engineers and system operations. Our background is, some of us are from engineering background, while some of us are from MBA backgrounds. So we divided our work accordingly based on our domain, but still we contributed equally in all the domains. So can you move on to the next page? Oh, sorry. My team is, I'm Pujangi. We have Swapna, Krishna Madhur, and Venkatadri. Yeah. Can you move on? Yeah. So our final model, we used CAD tools regressor, LGBM, random forest, LGBM with 3D objective, and we used model all these models together with RIDCB. Most important features that we found out were, we did some 2-3 steps to gather to or come to this these features. So that were cancer diagnosis code, payer type, patient zip, state, age, description, and metastatic cancer diagnosis code, and if they are self-employed or not. Tools used is, language was Python, but to write the notebook and share between us, we used Google Colab. Total time for training the model was around 61.89 seconds. Can you move on to the next? Okay, next one. All right, so first step was feature engineering, which was very important, which we found very interesting and crucial to change the RMSEs or improve the performance. For data cleaning, we went on one by one for each of them. So first of all, we had few columns like metastatic diagnosis treatment type or BMI, etc. So Swapna from our team, she did some research on the metastatic cancer to understand or get some intuitive insights on what features to select and how to do the filling and all. So we got to know that BMI is not really much helpful in deciding whether the metastatic cancer is going to be there or not. So we decided to drop that. Plus, it has a lot of null values. So having some average or mean would introduce some noise. So that way we dropped. And metastatic treatment columns also we dropped. Then for some columns like payer type, we added most frequent value. And for breast cancer diagnosis description, we tried to extract keywords and create new features out of it, separate features, but we thought that they are not really helpful separate. But if we keep it collective, like directly encoding the breast cancer diagnosis description, it was adding more value rather than separate ones. So that way we did categorical conversion to numerical values for all the other categorical values as well. And to select features, first of all, we thought of getting the correlation between all the features and the target value, and that way try to manually pick up. But we expected some values like or some relation like y is equal to mx plus c. So if independent variable is going up, then dependent variable should go up or down, something like that. But as we did some EDA, we realized it is not necessarily going to be this way. Or if the patterns or some tree going to be there for algorithm, it doesn't really have to be in some format of correlation. Maybe some features work together very well, while some features for some values, they have certain values of metastatic diagnosis period, something like that. So we decided to follow other approaches, which was recursive feature elimination with SHAP values. So for all the models or algorithms that we used, we derived the most significant features with that. And then these and plus some other were the common features out of it. And then by doing some manual trial and error for the features, we derived these were the features we would like to go ahead. You can see breast cancer diagnosis code is having really good score. And so is with patient age, etc. So one more thing we found out was patients with age less than 40 are more likely to have metastatic diagnosis. So we created one feature as age 40 with having binary values, yes and no. But we realized we have to find the metastatic diagnosis period and not that whether it is detected or not. So we decided to go ahead with patient age rather than having age 40 or something. And for average temperature, which was very surprising for us, that first of all, for each of the models or each of the algorithms, we were getting a different set of average temperature columns. But and if we run one more time for the same algorithm, it would give different values for, again, the significant temperatures. We had used interpolate to fill out the missing values because we see for the average temperature, because for a given zip, of course, the temperature of the current month can be derived from the temperature of the other months for the same zip. That we fill out the values, but we found out, we thought that maybe adding the average temperatures might do the overfitting. So we decided to drop those columns. Can you go ahead to the next slide? So you can see this is, we've added, this is partial plot for top two features. So this is breast cancer diagnosis code. You can see from the range 0 to 9 or 10, the diagnosis period is higher. And for the rest of the diagnosis codes, it's quite lower. Can you go to the next slide? And for the age, we see there is some pattern, like in the beginning, it is quite high, but then it decreases and then again it's increasing. So this is where I said there is not going to be a line or something, but not a proper y equal to mx plus c equation, but some relation is going to be there. So we can't just rely on the proper correlation or the direct correlation. Okay, can you go to the next slide? Okay, so for the training methods, we used a lot of algorithms, CatBoost, XGBoost, Random Forest, LGBM, AdaBoost, etc., extra trees. But out of them, we found top 4 as CatBoost regressor, LGBM, Random Forest, and LGBM with 2D objective. And we use ensembling for this with the CV because we wanted to have a generalized model instead of overfit model, and getting insights from these top models was the right approach, is what we thought. And if you see the weights, you can see CatBoost is having around 16, while top second is Light GBM with 2D objective, which is around 9.47. And then third is Random Forest, which is 7.90. LGBM is quite low, but it has good RMSE, good accuracy. So we decided to go ahead with this. Can you go ahead? Next. Okay, so first of all, we decided that we don't want to overfit a model because, as I said, for average temperature, in some cases it would reduce the RMSE. RMSE was the factor that we used to evaluate the models. So it would reduce the RMSE, but it somehow felt like it is doing some overfit, or it may add some noise into it. So that was our main intention of the things. So when we use rich CV, that was also one of the reason why we decided to go ahead with ensembling rather than using our top model, which is CatBoost. So our public score was actually around 82.851, but our private score turned out to be around 80.626, which is quite a jump. So that could be because we focused on not letting the models get overfit. Okay, so can you go to the next slide? So our breast cancer diagnosis code, which contributed around 80%, I would say, for the performance, and CatBoost regressor had the highest share, but there was not much difference in the ensembling, but it was improving the regularization of the model. So we decided to have our final model as the ensembling, rich CV ensembling. Okay, can you go ahead? All right, so that was our solution. Any questions, please let me know.
Yeah, for sure. That's a great job not overfitting. It's good that you really put a lot of effort and a lot of emphasis on that. You mentioned you use Light GBM with 2D objective. Could you explain that to our audience? What is that and why did you use that?
Okay, so Light GBM is gradient boosting that we decided to use. But 2D objective is, first of all, when we were checking the data, we saw our metastatic diagnosis period had a lot of 0 values and also positive values. So we didn't know 2D objective anything about it, but somehow all of us had that thing like, oh, we should do something about it. We should note it down and do something about it in future. Because whatever data I had seen were like, I had once done some data analysis in the back, and it was like mix of data is there, like negative values are there, some fractions values are there. So we decided to use this, and we saw 3D objective has a pattern which also has similar symptoms, I would say, like 0 and positive skewed values. So we decided we should use it, and you can see in the final rich CV, it is having around 9 score or the significance score. So that is also a good conclusion we derived from the 0 values.
Well, outstanding. Thank you very much. I think you had a really good performance and really good presentation. And we learned a lot from your presentation. So thank you.
Thank you all. Okay.
Well, thank you all for your answers, for all of your hard work, and congratulations to all the teams for fantastic performance. And as you can see, each of the teams had a very unique approach towards modeling. Some of them did different researched on the medical background. Some of them focused on the modeling. and different backgrounds, different approaches towards feature engineering. And this is what makes this competition so remarkable, so interesting, is that we have different people and different approaches that people take, and we all learn and grow together. And I hope you all enjoyed the presentation, and invite you all to continue to be a part of the community, and look forward to your contributions in the future. Thank you so much.
Great. Thank you. Yeah, very well said, Sharda, and thank you to all of our winning teams. As you can see, everyone's come from such different backgrounds, and so we encourage you to always check out our WiDS Datathons. Really, wherever you come from and any knowledge you have, you can participate and try out our challenges. And so with that being said, this also concludes our global challenges for this entire 2024 season. Our next global challenges will take place next year, and we'll be sending out announcements in the fall to let you know what those are going forward. And the last thing I do want to mention about our winners is that all of our winners also have posted their solutions on the Kaggle discussion forum for this challenge. And so if you're interested in checking those out as a little bit of a resource for today's panel discussion, I'll put a link here in the chat, and you can click through each of those links to find and look at the Kaggle solutions posted from each winner directly on the discussion forums. So thank you all again for joining us on today's panel discussion. We'll keep the room open for a minute or two to share any final thoughts, and congratulations again to all of the winners. Thank you.
Thank you.